Here is a problem that looks like heavy machinery. In space, take the point 3, 2, 1. Take the line through the origin pointing along 1, 1, 1, a slanted axis, not a coordinate axis. Now rotate the point about that line by exactly 60 degrees. Both directions allowed. All coordinates here are real numbers. You could reach for rotation matrices. Half a page of sines and cosines. But look at the answers, 3, 1, 2, and 2, 3, 1. Integers, in fact, permutations of the point we started with. An answer that clean is a hint. Some idea makes this rotation a short, honest hand computation. And by the end of this episode, it will be yours. Here is the whole idea of this episode, in one sentence. Writing a point as s times a plus t times b is not just algebra. It places the point at coordinates s, t on the grid that the two vectors a and b draw, even when that grid is slanted. So you can solve problems on straight graph paper and carry the answer across. And one special case is golden. If the two axes have equal length and meet at a right angle, their grid is honest graph paper, and the point cosine theta A plus sine theta B is exactly rotated by theta. Coordinates first. Rotation for free. Take two vectors A and B, not parallel, and draw their grid. Copies of a one-way, copies of B the other. Any point of the plane is reached exactly once. So much of A, so much of B. 2, a plus B sits at coordinates 2, 1 on this grid. 2, a minus B, 2, minus 1. Minus a minus 2B, minus 1, minus 2. The letters S and T are real numbers. This is a full coordinate system, not just lattice points. When a textbook asks you to express a point in terms of A and B, it is asking for coordinates. Nothing more. Reading them off a slanted grid is the same skill as reading a street map that was printed at an angle. The payoff, hard regions become easy ones. A region is given by conditions on S and T. Say S and T non-negative, with S plus T between 1 and 2. On straight graph paper, that is a trapezoid between two triangles, area 3 halves. Easy. Now carry it to the slanted grid. Straight lines stay straight, and every area gets multiplied by one fixed number. The area of the parallelogram that A and B span, root of, length, a squared times length b squared minus the dot product squared. With length 2, length 3 and dot product 4, that factor is 2 root 5, and the region's area is 3 root 5. Draw straight. Solve straight. Multiply once at the end. The source material runs a heavier region through the same mill and gets 12 root 5 one factor, any region. Now the golden special case. Let the axes and B have equal length and meet at 90 degrees. Then their grid is genuine graph paper, and on graph paper, we know exactly which point sits at angle theta on the circle. Cosine theta, sine theta. Translate back. Cosine theta plus sine theta B is the vector A, rotated by theta toward B. In the plane, this gives the famous recipe. To rotate the vector a, b by 90 degrees, take minus b, a. For any angle, blend the two with cosine and sine. One test drive. Rotate the point 3, 3 about 2, 1 by 120 degrees. Shift blend, shift back, and the answer drops out in 3 lines. No matrix was harmed. Now let the rule leave the page, into space. In space, the origin, the point A at 2, 2, 1 and B at 2, 0, minus 1. On the plane through all 3, Draw the circle centered at the origin through A. A circle needs graph paper, so we build some inside the slanted plane. First axis, O itself length 3. Second axis, a vector in the plane perpendicular to OA. Every in-plane vector is S times OA plus T times OB. Perpendicularity forces T equals minus 3S, and the direction minus 4, 2, 4 appears. Normalize. Length 6S, so the unit vector is 1/3 of 2, minus 1, minus 2, choosing the sign that makes the x component positive. Scale it by 3, and we hold 2 perpendicular spokes of equal length 3, lying in the plane. Graph paper hanging in midair. Now the circle is one line. P of theta equals cosine theta times OA, plus sine theta times the second spoke. As theta runs, P sweeps the circle, always in the plane, always at distance 3. Our machine check confirms both, all the way around. And questions about the circle become trigonometry. The height of P, its z-coordinate, reads off the third components, cosine theta minus 2 sine theta. How high does the circle reach? That expression is a dot product of the fixed vector 1, minus 2 with the unit vector cosine theta, sine theta. So by Cauchy-Schwarz, it never exceeds the fixed vector's length, root 5, and equality is attainable. The top of a circle floating on a slanted plane in space, root 5. Found without ever leaving the graph paper we built. And now the opening problem. Rotate B at 3, 2, 1 about the line L through the origin along 1, 1, 1. A point rotating about an axis moves on a circle. The circle lives in the plane through B perpendicular to L, and its center is the foot of the perpendicular from B to the axis. Find that foot. H is on the line, so H is T times 1, 1, 1. Perpendicularity. B minus H dotted with the direction is 0. That gives 3t minus 6 equals 0, t is 2, and H is the point 2, 2, 2. The spoke from H to B is 1, 0, minus 1, length root 2. Center found, radius found. Now we need graph paper in the plane of the circle. The second spoke must lie in the rotation plane, perpendicular to the axis, and be perpendicular to the first spoke HB. Write it as a BC. Perpendicular to 1, 1, 1. A plus B plus C is 0. Perpendicular to 1, 0, minus 1. A minus C is 0. So C equals B equals minus 2. The direction 1 minus 2, 1. Match the length to root 2. The factor is 1 over root 3. As a check, the two 90-degree positions of B are the center plus and minus this spoke, and the Rodriguez rotation formula, run by machine, lands on exactly the same 2 points. Equal length perpendicular both in the plane. Graph paper again, this time hanging on a slanted axis. 60 degrees is now arithmetic. Rotated spoke equals cosine 60 times HB, plus or minus sine 60 times the second spoke. Cosine 60 is 1/2. Sine 60 is root 3 over 2, and the root 3 cancels the 1 over root 3 in the spoke. All the surds annihilate. 1/2 of 1, 0, minus 1, plus or minus 1/2 of 1 minus 2, 1. That is 1 minus 1, 0, or 0, 1 minus 1. Add the center 2, 2, 2, 3, 1, 2, and 2, 3, 1. The opening promise kept. A 60-degree rotation about a slanted axis, landing on integers by hand in 4 lines. The machine ran the Rodriguez formula as an audit, the same 2 points to the last digit. How far does the one idea reach? Any rotation anywhere. To rotate in any plane in space, through the origin or not, pick two equal-length perpendicular vectors lying in it, and cosine sine does the rest. Circles, helices, camera orbits, the same two spokes. In the plane, the same blend is the rotation formula every matrix book prints, and the complex numbers cosine plus I sine is this identical idea in different clothing. The honest boundary, coordinates need independence. If A and B are parallel, their grid collapses to a line, and no point off that line can be reached. A linear combination is a coordinate system exactly when the axes span. Whenever a problem hands you two good vectors, ask what it looks like on their grid, draw straight, solve straight, carry it back. One episode, one move, three payoffs. Read coordinates. S times A plus T times B is the point S comma T on a slanted grid. Straighten regions. Solve on straight paper. Multiply areas by the parallelogram factor once. Rotate for free. Equal-length perpendicular axes make cosine theta A plus sine theta be a pure rotation in the plane, on a floating plane in space, or about a slanted axis. Pick two vectors. Read coordinates. Everything else is arithmetic. Every grid is graph paper if you drew it yourself.